Well, hello, welcome to the Math 60 PowerPoint number 8. We're going to be looking at two variable equations. It's going to be similar to formulas, but we're heading towards chapter 3 with linear equations. So we want to start putting things in terms of equations we're going to see involving variables x and y. This corresponds to section 2.3 in our current textbook. Let's get started. So if you recall, a linear equation in one variable is written this way: ax plus b equals 0. Now, of course, you won't see the a, b. They're oftentimes numbers, but where a doesn't equal 0, because if a was 0, you wouldn't have an x term. And a solution to a linear equation in one variable is always any value for the variable that makes the equation a true statement. So it's always our goal when we have an equation, whether there's one or two variables, it doesn't matter, is to find the value of the variable that when you put that in, it makes it true. Now, when you only have one variable, here's an example of a linear equation, one variable, and there will be exactly one solution. That's what's somewhat unique to single variable linear equations. When we're looking for the value of x to make it true, we're only going to find that there's one solution. And you know by now how to solve these. Of course, moving the 15 to the other side, then dividing by the 3, and I'm sure you're able to get this. So we're going to find the solution to that. See what you get. I know when I worked it out, I got a solution of -3. Is that what you got? Because 3 times -3 is -9 plus 15. -9 plus 15 is 6. Now, what we're going to think about today is what if we had a linear equation in two variables? It would look like this. First of all, there would be a term dealing with x, but there's also then a term dealing with y. So ax plus by equals c, where a and b are not both 0. We're going to see a little later that it might be possible that one of them ends up being 0, but we can't have both being 0. And so in this form, a solution to this type of an equation in two variables will be an ordered pair. In other words, since we have two variables, x and y, then together there'll be a value for x and a value for y that makes this equation true. So they're always going to be written in ordered pair form, both x and y together. We'll see plenty of examples here today. And since we have a different looking solution, an equation in two variables will have infinitely many solutions. We're going to find that we're not just going to find a single solution, we're going to find many. For example, here would be a typical type linear equation in two variables: 3x plus 2y equals 6. This is an example of a linear equation in two variables, and there will be infinitely many solutions, and we're going to spend some time looking at those. So let's start that right now by looking at our first example. Here in our first example, we're asked to find 4 solutions to the equation 3x plus 2y equals 6. And they're going to kind of hold our hand through this at the beginning, and they're going to say, okay, if x equals 0, what is y? And you'll see over here, and we're going to talk about this as we go through, one of the ways to help us organize our work, or at least certainly organize our solutions, is to have this table of solutions that we can write. So by putting a 0 here for x, we're really starting to ask the first question: if x is 0, what is y? And we're going to see how to solve this in just a little bit. I was just going to give you some kind of thoughts and some visualization as to where we're going with this. And then, of course, if x is 0, we could ask the same question: what happens when y is 0? And so we designate that in our table by letting y be 0. And we're going to go ahead and solve this, and you'll see the table completed as we go. But of course, we're not confined to just letting x or y be 0. They can be any number we want. So maybe we want x to be 4 or y to be 6. So let's look through some of these. So here's our first one. There's our equation: find 4 solutions to 3x plus 2y equals 6. And let's start with that x equals 0. If x equals 0, what is y? Now, that implies then in our equation that the value of x, at least for the first solution, the x part of our solution is going to be 0. So we literally take that value of 0 and we put it in for x, as we did here. And when that happens, of course, 3 times 0 is 0, so that just falls away, and we're left with the equation 2y equals 6. Now, you by now certainly know how to solve that. We divide both sides by 2. We get that y equals 3. So now is where we need to gather our two different variable parts into a single solution, because remember, we started off with x equals 0, and when x equals 0, then y equals 3. Together, those make up a solution. So we write it this way as an ordered pair. This is called an ordered pair, x, y. We write 0, 3 is a solution. And what that means is, given our equation, if x is 0 and y is 3, then 3 times 0, 0, plus 2 times 3, 6, equals 6. So 0, 3 is a solution. But as we're going to see, it's certainly not the only solution. So next we're going to say, okay, well, what if y is 0? What is x? So here we're going to put 0 in for y, just literally replacing it. Now, of course, 2 times 0 is 0, so we're left with 3x equals 6. We want to solve for x now, so we divide both sides by 3 and we get that x equals 2. Then we remember x equals 2 only when y equals 0, so together we make that into a single ordered pair solution. When x is 2, y is 0 is a solution. So now at least we have two different solutions to the one equation. And of course what we're going to find is there are infinitely many, so we can make as many as we like. So now we're going to continue with that. We've found our two solutions, 0, 3 and 2, 0. We're going to continue on. I'm just going to try to make use of the table a little bit to get organized, and we're going to ask it this way. What if we wanted x to be 4? Well, if x was 4, then we're going to put 4 into the equation for x, and you're starting to see how this works now. But now the first term, 3 times 4, doesn't fall away because it doesn't equal 0, so 3 times 4 is 12. And now we continue solving like you and I learned how to do in the last chapter, solving for y. So here we're going to divide or subtract both sides by 12. Which gives us negative 6, and then we're going to divide by 2, which gives us negative 3. So when x is 4, y equals negative 3 becomes the second part of that solution. So the ordered pair, the solution is 4, negative 3. Let's do one more. It asks for 4. Let's do one more. So the last one now, we're going to say, okay, well, what if y is 6? Well, if y is 6, we go up to original equation and put 6 in for y. Of course, that gives us 12. So we have 3x plus 12 equals 6. And again, we're left to solve for the x variable value. We do that by subtracting 6, dividing by 3, and we get that x equals 2. And of course, that's the x value that goes into our table and gets put together, joined together with the 6. So we would say that this is our ordered pair solution. So there's 4 solutions to that equation, and we could continue on choosing any value, putting it in for any of the variables, and that's what it looks like. So here are our 4 solutions. In this example, we have the 3x plus 2y equals 6. We have our table of values. So the solutions themselves are these ordered pairs that come straight from the table. And so as we're going to see shortly, maybe you've discovered, the calculator that we use, the Texas Instruments calculators, have a very convenient way of taking an equation. First, you have to solve it for y, so like you're solving a formula. Enter it into your calculator, and then you can look at the table feature on your calculator, and the table will give you not only 4 solutions, it'll give you infinitely many solutions as you arrow up and arrow down to see more and more solutions. But they are all ordered pairs. Each of them individually is a solution to the original equation, meaning that when you substitute the x value in for x, the y value in for y, you make that equation true. So let's have you practice some. If you'd like, you can pause this video, and here's a different equation, 2x minus y equals 8, and they're asking for 2 ordered pairs that are solutions, and they give you some values to start with. Okay, hopefully you've given this a try. Let's walk through this. What they're implying here at the start is that x equals 4, so we're going to take our equation and we're going to put 4 in for x. And once we do that, we're left with just a single variable y. We want to now solve for that. So 2 times 4 is 8, minus y equals 8. We want to get y by itself, so I'm going to subtract 8 from both sides. And when I do, this goes to 0. So I have negative y equals 8 minus 8 is 0. Now I want to get rid of that negative just so that I've literally solved for y. I'm going to multiply both sides by negative 1, and of course negative times negative is positive. Negative 1 times 0 is still 0, so that didn't change it. So y equals 0. Now y equals 0 when x equals 4, so we would put those together as an ordered pair solution. Now likewise, the second one is implying that we want y to be 4. So we take the same equation, 2x minus y, but in place of y, I'm going to put 4. And now I'm going to look for the x value that goes with y equals 4 to make a solution to the equation. So solving for x, I'm going to add 4 to both sides. Hopefully you did the same. And I have 2x equals 12. And then dividing both sides by 2, we get x equals 6. So x equals 6 is part of a solution together with y equals 4. So we would write it here. And together that ordered pair is a solution to our original equation. Now here's again what our linear equation in two variable looks like. It's ax plus by equals c, where a and b are not both 0. We just want to make sure that we don't lose this term and this term if a and b were both 0. But here now let's look at a kind of a unique equation, but ones you're going to see, and that is, well, if they can't both be 0, what happens if one of them is 0? So here's our next example. Let's find 4 solutions to this equation, x equals 6. And at first look, this doesn't maybe feel like an entire linear equation, but it is. It just happens that it doesn't have a y term. So that implies that b must have been 0, but a isn't. So we still want to find solutions to this. So we need to recognize that in this linear equation, the variable a is a 1. That's okay. It doesn't have to be. It could be a 2, a 3, or a -2. b is 0. In this case, c is 6. And so when you put a 1, a 0, and a 6 in there, you see this term here is just going to fall out to 0. So that's what actually gives us that equation. Now let's go find the 4 solutions, and let's start with the first one. Again, we've seen this now. When y is 0, well, starting with our original equation, when y is 0, we put it in for y, but of course 0 times 0 isn't going to change that second term. And guess what? We get x equals 6. So when y is 0, x is 6. That's a solution. Going on to the next one, well, what happens if y is 1? Well, here's our equation. If we put 1 in for y, again, 0 times 1 is still 0, and guess what? X equals 6. And as we step through this, you'll begin to see it really doesn't matter what value y takes on. If y is 4, x is 6. If y is 100, x is 6, because every time we put 4 or 100 in for y, it's still going to be multiplied by 0, which makes it 0. And so we can come up with infinitely many solutions. And if you look at the pattern with a simple equation saying y is 6, it's essentially implying it doesn't matter what y is, x is 6. I think I might have said y there, sorry. X is 6. It doesn't matter what y is. So a solution will always have 6, and then it doesn't matter what y is. It could be 1,000 if we want it to be 6, and it could be -5. It doesn't really matter what y is as long as 6. So we can come up with infinitely many solutions rather easily. And in chapter 3, we'll look at when we graph these, they'll have kind of a unique look to them also, and we'll be able to identify them. Before we're done, let's just quickly look at an application problem dealing with these kind of equations. Here in this example 4, Oregon's population in millions can be approximated by the equation y equals 0.027x plus 3.819, where x represents the number of years since 2009. So this is an equation that measures our state's population since 2009. It says, use the equation to estimate Oregon's population in 2013, and then interpret your result with a complete sentence. Okay, well, let's start with the first part, 2013. That means that our variable x, because x is the number of years since 2009. It states that really well for us here. We know what our variable is. So 2013 minus 2009, that's only a 4-year difference. Therefore, in this case, we want x to be 4. And so we're going to take our equation that gives us our population. We're going to put 4 in for the number of years since 2009, so x equals 4. And now it's simply just using our calculator, since they're decimal numbers, to calculate what y is. And when we do that, we get 3.927. So that's our answer when x equals 4. In the year 2013, our population is 3.927, but remember, our population is given in millions. So now let's interpret this. According to the model, we estimate in 2013, Oregon's population will be about 3.927 million people. And so that's how we can make use of that. Let's look at the same example, but asking a little bit different question. We're going to use that same equation to estimate to the nearest year when Oregon's population will be over 4 million people. Interpret your result with a complete sentence. So now, rather than giving us the year and asking for population, here they're giving us the population and they're asking us for the year. So 4 million people means that Y now, remember Y is our population, Y is 4. And so we take our same equation that represents population in Oregon since 2009, and we take that equation, Y equals 0.027x plus 3.819, and we allow Y to be 4. Now in this form, when Y is 4, our interest is in determining X, because remember, it's asking to find the nearest year when the population is at. We're looking for X. So we subtract 3.819 from both sides, and we end up with our equation 0.181 equals 0.027x. And then solving for x, we're going to divide both sides by that 0.027. By now, I'm sure you guys are getting more comfortable in doing this. And when we do that, we find that x equals 6.7. And now we want to know in what year, to the nearest year at least, nearest meaning that we're rounding off, we're going to go over 4 million. And so 6.7, that's approximately 7. I'm rounding up because of the 0.7 here. So after about 7 years, so let's interpret this with a sentence. According to the model, we would then estimate that Oregon's population will be over 4 million people in the year 2016. And again, why 2016? Because this is measuring it since 2009. So 2009 plus those 7 years puts us at 2016. That's how I came up with the year. So again, with this particular example, where y equals something, it'd be easy to enter that in our graphing calculator under the y equals screen. And then once you do, you can hit the table feature on the calculator and you can find all the different estimated populations for all the different years and kind of confirm some of the answers that we got on that last example. So in summary, linear equations in two variables take the form ax plus by equals c, where a and b are not both 0, meaning you're at least going to have one of those terms, but most often we'll have both terms, a term with an x and a term with a y. A solution to an equation in two variables is going to be an ordered pair, and ordered pairs always take the form x followed by y, and together the two values make a single solution. An equation in two variables will have infinitely many solutions. There's not just a single ordered pair that makes an equation true. There are going to be infinitely many of them. And one way to keep things organized is that a table is helpful to organize our information. Your graphing calculator has a table feature built in, and I hope you learn to use it. Well, I hope that helps.